quick set of notes, but a good set of notes here. We are going to expand on what we talked about in our last video about the least squares regression line and looking at that graph. What we're going to do is we're actually going to create one on our calculator today. And so a couple things before getting into the calculator part. We're talking about correlation and regression. So what we can do with that is it describes linear relationships. So there's different types of relationships. In chapter 4, we were talking about normal curves, so that wasn't linear. That was a curved relationship. But this specifically, as we've been talking about throughout the chapter with like the backpack example and different examples that you've seen, is only for linear relationships. So for example, a child's growth from 3 to 8 years old is actually a linear relationship. Typically, again, there's outliers always, but typically follows a linear relationship. And so, when you're 3 years old, your doctor could theoretically make a prediction of how tall you're going to be when you're 8. Now, typically, we don't need to be that exact, so that's not a practice that they do, although they can use, if you're only a certain height at 3 years old, and that might be a precursor for other problems or something like that, so they have that data for those reasons. Or, at 5 years old, if all of a sudden you've stopped growing like you quote-unquote should, again, that would be a sign to them that there's something that we need to look into there. So, but anyway, so your child's growth or a child's growth is linear from about 3 to 8 years old is what we found. But then, of course, once you hit, like 25, where you've probably maxed out, you're not growing anymore, and in fact, you're shrinking at some point, it's no longer a linear relationship. And same thing in that range. At some point, I'm guessing you've probably already hit it, but if you haven't, at some point you hit a growth spurt. And so at that point, you're growing more exponentially. You're growing at a faster rate than you normally would, which, again, makes it not linear. Again, correlation and regression are strongly affected by outliers. As I've said before, there's not one good data point that will explain a whole set of data for reasons like outliers, but something to be aware of is that can be affected by outliers. The least square regression line passes through the mean of the x value and the mean of the y value, which is more or less just a kind of a fun fact. I find that that's an interesting little thing that happens. And then switching x and y will affect regression, but not correlation. So it will affect your regression plot, but it will not affect your correlation between the 2 points. Okay? And so if we look back at that example, again, just to go over what a residual is the vertical distance between the data point and then the regression line. Again, that distance is called a residual. Okay, so these like vertical lines that you see that I've kind of bolded here, those are called residuals. So the residual is calculated by taking the observed y value, so the observed is like the actual data point, and then subtracting it from the predicted y value. And the predicted y value would be any point on this green line. And again, the reason why it's y, if you think about it, the y-axis goes up and down, and the distance is a vertical distance, so it goes up and down as well. Okay? Now, this can be shown a lot easier than this. I mean, this is a pretty good representation, but on your calculator, we can actually make a residual plot. Okay? So I'm going to use that data that we had, that we've been looking at with the body weight and the backpack example. Okay? So again, throughout this process, if you need to hit pause to complete a step or whatever, by all means, go ahead and do that. But I have my data in, if you cleared yours out, again, hit pause and make sure you get that data in there. Okay? And so I'm going to kind of follow the button by button here, but again, on your notes, you have the steps right there on how to do that. But if I go to second, y equals, and I actually already have it in there, but I'll go through this whole process as if it wasn't. Second y equals, and hit enter on plot 1. Okay? First of all, let's turn that plot off. Make sure it's on off right now. And then this probably says for you, if you haven't changed it, it probably says L2. But we want it to have that residual in there. So if you clear the Y list and then go to second again and stat, okay, and you need to scroll down, or if you just scroll up, it's at the very bottom of the list. So scroll down a bunch or just hit scroll up once, and you should have resig there, and hit enter. Hit enter just to make sure it goes through, and then let's see, if we hit graph, let's see what it looks like right now, okay? So we just kind of have our standard graph there. If I hit zoom and 9 for zoom stat, it didn't work. Why did it not work? Let's see here. Let's try turning our plot on. Maybe I switched that around. If I hit zoom 9 now, there we go. I'm sorry. Make sure your plot is on. To quickly turn on your plot, just go to y equals, scroll up, and see how that black box is around it? That means my plot is on. So if I scroll up and hit enter again, it turns the plot off. I apologize. We need the plot on there. Now go back to graph. And again, if you don't have this picture, hit zoom 9 and it'll default to that for you. And so now what this is showing is just the vertical distance for each data point. Okay, so this is, when we were looking at this plot, this showed, let's see, go back, there we go. So the difference between the two graphs, this is the actual like line of best fit graph. This is our actual scatter plot, where these are the different data points, okay? Compared to this graph is just the distance. This is showing, again, this is called a residual plot, because this is just showing the distance from the line. So for example, looks like, let me go to my window here and see, okay, everything is counting by ones. So if I go back to my graph, if I look at this coordinate right here, this plot, what this point represents is that it is 1, 2, 3, 4, and a decimal. Let's call it 4.8 or so. So this value is 4.8 units away from the predicted value. So the observed, which is this, represents this coordinate, is 4.8 units above the predicted. Okay, this one is about 3 below the predicted. This one is about 1 below, 2.5. This one is right on the predicted. So if I go back here, you see how this point right here falls almost on the line? That point corresponds to this data point here, where it's super close to the actual predicted value. Okay, and so again, the point of this plot is to just show the distance of these. So if we had a lot of blue points in this case that were right on the line here, that would mean that there wasn't a lot of residual. That would mean that the predicted line was very good compared to the observed values. Okay, so again, this just shows a clear understanding of the vertical distance between the observed and predicted values of your data. Okay, that again is called residual, and this is your residual plot. We have one piece of data that summarizes this, which is called your R squared. So we know R is correlation. R squared tells you how well the correlation matches the predicted values. And so the closer R is to 1 or -1, the better R squared will be. Okay? And so quite literally, you can read this as a percentage. So if I go stat, go to my one variable, okay. Oh, no, sorry, I'm in the wrong mindset here. Let's go to my lin reg. Okay, let's try that again. Okay, so my R squared for this data set is 0.474, all right? And so literally what that means is that my 47.4% of my data is explained by the pattern by the relationship that we found by body weight. So then the other 53% or so is explained by other variables like maybe the person weighs more just because they're out of shape, so giving them a heavier backpack isn't good. Maybe they're just not motivated. Maybe they're a little bit lazier. They don't want a heavier backpack. So 53% would then be some of the other observations that or some of the other factors that maybe we're not doing right there, okay, or considering right there, okay? So again, that's R squared. That's what, so R tells you the correlation, all right? So we have a decently strong correlation here. And then this tells you how well the correlation explains the data. So almost 50%, okay? So again, a quickie but a goodie there. 5.9, just interpreting residual and residual plots.